Okay, so now in the previous video we were looking at pressure in gases, and we saw that it is mainly due to the molecular collisions of the atoms with the walls. And so now we are going to look at pressure a little more, and the idea is to realize that there are two contributions to the pressure. One is, of course, the thermal contribution due to the random motion of the particles. They collide with the walls and they produce that pressure. The other contribution is due to the gravitational pulling down, right? So the gravitational force that changes the pressure as you go up. So let's look at this picture here, and this is the Earth. So right here at sea level, right here at the bottom, the pressure is going to be greater than the pressure here because of all the weight of the Earth on top of this line here. So this allows us to define a new unit for pressure, and that is the standard atmosphere, an ATM, and that is 101,300 Pascal. That is an ATM, or 101 kilopascal roughly. And a standard atmosphere is what we use a lot in the lab. It's the pressure that you're feeling, or close to the pressure that you're feeling right now on you, and it's due to the weight of all the air on top of you, basically. So if you hold your arm out, right, it has a surface of roughly, well, 10 centimeters. Let's just see it. Your arm has a surface of roughly 10 centimeters by 20 centimeters. That is equal to 200 centimeters square, which is 0.02 meters square, right? So what is the weight in newtons and in pounds of the air on top of your arm? Well, let's just calculate that force. That force is the pressure times the area. The pressure is what? Well, it's 1 ATM. 1 ATM is 101,300 Pascal times the area, which is what? 0.02 meters square. So this is equal to roughly, well, 1 Pascal is Newton per meter squared, so this is going to cancel here. So this is roughly 2,000 newtons, roughly. So and 2,000 newton is 450 pounds. So 450 pounds is the weight of the air on top of your arm if you extend your arm, right? So why isn't your arm being crushed? Well, because the pressure is exerted in all directions. So there is, if this is your arm here, right? So there is the pressure, the force due to the air on top of your arm, but then there is the same pressure at the bottom, and these two cancel out. So that's why you really are not holding that much weight. What you're doing is basically just your body is used to this pressure here, and it is, these two pressures are canceling out, so the net force is close to zero. So let's just look at the pressure in liquids, and let's just define hydrostatic pressure. And if we look at, assume that we have a liquid here, and we want to study what happens to this cylinder of water. So this is like a cylinder of water, right? So it has an area A and a height D, that cylinder of water. And so what are the forces acting on this cylinder of water? Well, there is the weight, of course, there is the weight of the cylinder of water. There is a pressure coming from the top. At the top you have P0A, right? So that is the force coming from this pressure. And then there is a force coming from the bottom, right? Due to this pressure PA. And this is what we want. We want to find the pressure at a distance D from the top due to this cylinder of water. So if we draw a free body diagram, what do we have? We have the mass the pressure from the top and the pressure from the force from the pressure from the top and the force from the bottom here. And these three have to be equal to 0 because this cylinder is not moving up or down. And from this equation we can write that the force at the bottom is equal to the force at the top plus the weight. That is what must happen, right? So this guy has to be equal to the two forces pulling down, so for these to stay in equilibrium. So now if we write the volume as A times D, the volume of this cylinder of water, that is A times D, and the mass is the density times the area times D, then what you get is, when this can be written as PA is equal then to P0A plus the mass, which is rho A D G, and then I can cancel the A's here, and then I get this equation here. I get that the pressure at the bottom is equal to the pressure at the top plus the density times gravity times D. So the pressure at the bottom only depends on this distance D. And this is the equation for the hydrostatic pressure that depends only on this distance D. So an application of that would be this one. Imagine that you have a liquid, right? And that liquid is connected. So a good question would be, is it possible to have a situation in which D1 here is going to be different from D2? Is this possible? And the answer is no. This is not possible, simply because, well, P0 is the same up here for both. So then you would have P1, right? The pressure down here at some point would be equal to what? Would be equal to P0 plus G rho D1. And then here you would have P2, which is equal to P0 plus G rho D2. And then what that means is these two pressures would be different, right? Would be different, and then that would mean that there's going to be a flow. So what this is telling you is that the only possibility is that the liquid is going to stay at this level. What can you say about the pressure at points 1 and 2? P1 greater than P2, P1 equals to P2, or P1 less than P2? Take a minute. And the answer is P1 is equal to P2 because they are both at the same distance. Another question. Is P1 greater than P2 here? No. It can be, right? The pressure is the same at all points in a horizontal line, and we saw that. The hydrostatic equation depends only on the distance, right? So you have an iceberg here that is floating, right? And then you have point 1 and point 2. So there's a big mass here on top of 1 and there's nothing on top of 2. Question, is P1 greater than P2, P1 less than P2, or P1 equal to P2, or P1 less than P2? Take a minute to answer the question. And the answer, of course, is that P1 is equal to P2. It doesn't matter that this iceberg is here on top of this point, right? This weight is not going to change the fact that along this horizontal line, the pressure is going to be the same. So what can you say about the pressures at points 1, 2, and 3? P1 equals P2 equals P3, and so on. Take a minute to answer the question. So what we are going to find is that these 2 points are at the same level, so they have the same pressure, and this point here is up there. Okay, so this has a less pressure than 1 and 3.